opportunity to give you a speech about quantum computers and quantum programming, and my very first question, who has heard at least something about quantum computers? Alright, and who thinks that it is our future? A bit less hands, but still. Some people believe. Okay, let's see whether your opinion will change today after my talk. And just to give you an idea how it will look like, well, it will be a little bit of everything. So to give you a general idea and impression about quantum computers, quantum programming, and what is the current state of it. So after this talk, you won't be an expert who will be able to program quantum devices, but at least you may get ideas how it will look like, and maybe where you can start also to do something in order to reach levels where you can actually program real quantum devices. So there will be a lot of slides, so let's start. And the first thing is a quick snapshot to give you an idea why we are actually speaking about quantum devices and where the ideas appear. So it turns out that there are physical limitations. So you know our transistors that make our classical computers smaller, fitting now in our pockets like smartphones. So there are still limitations, and at some point these transistors they will be of the size of the atom, and we cannot get smaller ones. So we need probably some other technology. In quantum case, it is not the idea that you will have even smaller electronical pieces that would serve the same purposes. Instead, we may think about quantum effects that may provide some benefits, additional resources to perform some computation more efficiently. So the need to look at some alternatives was one of the inspirations to consider quantum computation. And so the idea appeared already in the 1980s, and there was the following discussion. We cannot simulate quantum mechanics efficiently on any classical device. So there are some technical difficulties. And so this was the main motivation to produce the quantum computer. So let's make a device that would efficiently simulate quantum mechanics. Currently existing classical computers can efficiently simulate classical physics. Like those of you who played some modern computer games like racing ones, for example, they try also to implement physics efficiently. Okay, so quantum mechanics, well, it won't be possible to do it efficiently, so we may need to switch to some other paradigm. And so there was theoretical investigation that yes, probably it should work. The question then is how to perform it practically. And we'll speak about it a bit later, but here is one of the ideas why there are difficulties to simulate quantum mechanics efficiently. So you can see here some numbers. Suppose that you have a single bit of information. Then there are in total two different possibilities, 0 and 1. For 2 bits you have 4 possibilities, for 3 bits 8, and so on. In case of quantum system, for this example, if you have just 3 particles, you can have any of these 8 possibilities, or even something in between of those. Therefore, in order to describe this system, you need some number for each of these possibilities. So you see, you have just 3 bits, you already have 8 numbers to track in order to follow the evolution of quantum system. And so this number grows exponentially. So who can imagine how large is that number below the molecule of penicillin? Unimaginably large, right? So actually this number is so large that it is more larger than the number of particles in visible universe. And now imagine if you would have a quantum system consisting of 286 particles, you would need that many numbers to track in order to perform simulation. Therefore it shows that indeed there are physical limitations. We will not have enough particles just to store this information. And so this is one of the motivations. And why there is molecule of penicillin, actually in order to simulate all the quantum properties you would need roughly 286 particles, therefore you would need to follow that many different configurations at the same time. So if we have quantum simulator, we would be able then probably to develop new drugs for treatment, develop new materials, some more advances in chemistry or biology. And so later, after investigating the properties of quantum particles, it turned out that some of the properties can be used for advantage, so that you can perform some calculational tasks more efficiently. And one of the examples is famous Shor's algorithm. So it is about factoring some numbers. If you have two large numbers and do multiplication, well, you can efficiently calculate the outcome. The problem is if you get some large number and you try to factor it into its components. So this is believed to be a very hard task for our computers, and so currently there still does not exist any efficient algorithm. And this is the thing on which many cryptographical systems are relying. So, for example, RSA algorithm. And so this is the thing where there appear doubts that if we invent and build a quantum computer, then all our cryptography will be very vulnerable. So this is thanks to Shor's algorithm. It gives exponential speed up, therefore it allows us to factorize large number almost as fast as doing the multiplication of two numbers. And so idea of exponential speed up is that if in the past you needed millions of years to break some code, afterwards it will be done in some minutes or even seconds. So this is the second motivation. The third one would be applied to some more general tasks in our everyday lives. So there exists Grover search algorithm, and the idea is that you can perform search in unstructured data quadratically faster. It's also quite huge speed up. In some cases, again, several days can become several minutes, and so it will be very practical, especially if you need to work with very large amounts of data. So those three examples were some of the motivations why we actually need to build physically, theoretically described quantum computers. So let's shortly speak about basics of quantum computing. So where are the differences from classical ones? So classical computation relies on the concept of bit. Bit is the smallest useful unit of information or memory. So bit stores just one value. It can be either 0 or 1, so like binary value. You can think of it like a lamp. If it is switched on, then the value is 1. If it's switched off, then the value is 0. So we can have one of these two possible values. And that's it. If you have 2 bits, then you have one of the 4 possibilities. So manipulation with these bits is then transformed into our daily life computations, like summation, multiplication, processing of images, and so on. All comes down just to bits. Whether we can obtain some difference in case of quantum physics? Well, if you have a quantum particle, it turns out that it behaves both as a particle and as a wave. So like you can think of it as some solid object, like a ball, or a wave, which like lights that we usually observe, or some sound waves. And so there is so-called duality in quantum mechanics. So where light can behave both as a particle and as a wave. And it produces some interesting effects. It turns out, overall, things that express quantum properties, they can be in a superposition. So if we turn back to concept of bit, it was either 0 or 1, so we're certain about where it is, like it is a state. In quantum case, it can be in multiple states at the same time. So some people describe it as it is like simultaneously being 0 and 1 at the same time. From physics, you can think of like you're not sure where the particle is located currently, but it's certainly somewhere there or there. So it's one of the ideas how we can think of superposition. And if we have a superposition, we're not certain where it is, but when we do a measurement, if we observe the particle, so if you look at the particle, it will appear at some exact point. If you don't look at it, it's like 0, Z. So who has heard about Schrödinger cat experiment? Alright, as I see, it's a very famous experiment. So, while you're not observing, you're not certain about the state of the system. Whether cat is dead or alive, whether your bit is in state 0 or in state 1, whether the particle has hit the board in that place or in another place. But when you look at it, you will observe it in exact location. And after observation, by the way, if other people also will look at the system, they will observe the same outcome. So now it becomes certain where it is. So the state becomes certain. And so this is the event of measurement. And by considering these two interesting properties, we can think about the qubit. So we are able to manipulate with some particle which possesses these quantum properties. One of the examples could be electron, which is spinning, and so it can be spin up or spin down, representing state 0 or state 1, like for a bit. And at some point it's spinning in a superposition, so you're not sure whether it's spin up or spin down. And mathematically it looks that complicated, so it can be in superposition, which is described by some numbers attached to state 0 and state 1. These numbers can be transformed into probabilities. Summation of all probabilities should be equal to 1. So therefore, if you observe your bit, it should be either state 0 or state 1. So certainly it will be one of these possibilities, but probabilities will depend on these two numbers to describe the system. So this could be an example of a quantum particle. You can have a photon which goes through a beam splitter, so it can be polarized in a way that either it goes through or it is reflected to the top. And so this beam splitter is designed in a way that our photon is polarized such that with equal probabilities it either will go through or go up. So this is an example of quantum experiment with a single photon. By the way, such polarization is also used in our sunglasses, which allows us to compensate the effect of bright sunlight. So superposition is one of the effects that could be used for advantage in computation. The second interesting quantum property is called entanglement. So two particles can be correlated together, and even if they are separated by some distance, they still can affect each other. This allows us to prepare more complicated quantum systems and use even these properties for secure communication on large distances. So one of the examples could be that you have two particles, then you locate them in different cities, and there are two people. And suppose that particle was correlated in a way that it is in state 0 and in state 1 with equal probabilities, like 50-50. If party on one side will measure the particle and will obtain state 0 or state 1, the second party on the other end of the communication will observe the same state. So like the first check will be random, it is either 0 or 1, but since the particles are affecting each other, the second particle will be in the exact same state. So you can imagine how this could be used for communication, but also it is beneficial for some computational processes. So maybe this is the future of our communication when we have entangled quantum states. So here you can consider three particles, and we have three different stars, and suppose that there are some planets orbiting them, and there is one person on each of the planets, and they are somehow communicating by using these three quantum particles. Alright, so now we have a very brief idea about quantum particles and that we can use them as a qubits, so which are possible to be different states simultaneously. How do we build a quantum computer from it? Of course, it is important to learn how to manipulate them, and this is one of the most challenging things in building a quantum computer. But overall, let's check the main idea. So, in essence, quantum computer is just array of the well-controlled qubits. So if you manage to have these quantum particles and you're able to control them in a predictable way, reliably, then it is possible to build a quantum computer. So in the beginning there is a small number of qubits, but maybe later we'll expand and then we'll be able to use it for some larger tasks. So of course, in order to observe some information from your quantum system, you would need to perform a measurement. So you need to observe the particle to conclude whether it is in state 0 or state 1. So we will not only need to have a controllable qubits, but we will also need this measurement. And also we need, as for any device, we need to provide input in some way, and we need to get some output by this measurement. So now you can guess that we will have some quantum particles, we control them, but at the same time we have classical component like our regular device, where we do queries to our quantum system and we observe some outcomes, and we can later also do some classical post-processing. And this leads to the possible process of quantum computation. You prepare the data for a quantum unit, then you use your quantum unit to process this data, you do the measurement so you obtain the outcome, and then you process this result classically. So you observe some regular data, you did whatever you wish with it, and maybe from it you did a conclusion that you need to launch your quantum device once more, maybe to get some extra information or do next steps. So this is a possible process of quantum computation. And this is how the quantum computing process can look like. Who is familiar with images like the top one? So in short, it is the idea of digital circuits, and this was the basic idea of how to perform computation with bits. You have a CPU in your computer or in your phone. It consists of a lot of such circuits, and they process signals. You send additional signals in order to program them or in order to ask for some operations, but overall it is the foundation of the idea of computation. Like, the signals go through these digital gates, and so they change the bit value, zeros and ones, and so this can perform some fixed calculation. In case of a quantum device, we can use the similar idea. So like you have a digital circuit, but this time each operation represents quantum transformations. So the ones that affect the state of your quantum particles. So you can see here, you have lines, each line represents a quantum particle, and boxes represent the operations that are performed on these particles. So this is called quantum circuit. It is like instruction in which order which operations to perform on your quantum particles. So this is more detailed example. So if you would like to analyze very deeply quantum computation, it is good to understand also vectors and matrices. Overall, it is possible to do calculations also without them. It just gives you the whole range of the control. So you have your two quantum particles, and then there are two operations that can be described with the help of the matrices. Matrix just describes how one state is transformed to the other. You can think of this as conditions, like if, else, for each of the possibilities. If you would have many particles, then this matrix would be very large. But you can imagine then, if else number of constructions would be quadratically larger, so therefore it is still quite complicated to describe it. So yes, this is how it can look like. Here we created correlated two particles. This was the example where I said that if you measure one of them in some state, the other one will be in the same state. So either yellow or purple, for example, representing 0 and 1. And this is how a quantum computer may look like, which allows us to perform calculations with the help of quantum circuits. This is an example of IBM device. So quantum chip is somewhere there. You can see the arrow. It is all held in very cold environment. in order to remove possible interferences and uncontrollable effects on your quantum particles. And so by these wires you send signals in order to perform these manipulations of quantum particles. This was the first paradigm, and second paradigm for quantum computers is called quantum annealing. So idea is that if you prepare specifically your quantum system, it will evolve in a way to try to find the state where it has the lowest energy. So it can be described by excited and ground states, but you can think of like you have some system and it tries to relax in the state where it has the lowest energy. So like if you're already laying on the floor, you cannot fall even more below, right, at this point. But if you're sitting on the chair, there's slight possibility that you can fall from it, right? So here, the idea is that the system really tries to find the most stable point, and it is the point with lowest energy. So in classical case, there might be difficulties that you cannot find the state with smallest energy. In quantum case, there are some effects that allow sometimes to do it more efficiently. Here you can see example of quantum tunneling. So for example, if you are falling, and you have fallen in the very first, this bottom part, it is not the lowest possible point. So you may get stuck there. In quantum case, it's sometimes much easier to get from this stuck point and get even lower. This lowest point later can be used to describe the solution to some of your tasks. And I will show very shortly how it may look like for a real problem. Overall, quantum annealers are not universal. So if previous example where we had quantum circuits allowed us to perform all possible quantum computations, in case of quantum annealing, it is, let's say, some subset of all possible tasks, and mostly it can be described as tasks which show us optimization problems. But it turns out we can adapt them still to do some useful stuff, not only to solve some optimization problems like how to visit all the cities by spending the lowest amount of time or making the shortest distance and still reach each of the cities. But also you can apply it to artificial intelligence, including also machine learning, signal processing, maybe scheduling tasks, like when you need to assign work to hundreds of people in order to do it the most efficient way. So it's quite a big niche, and quantum annealers, at least now, people try to use them to solve some daily tasks on larger companies. And this is example of quantum annealer. You have heard about email systems. 2 years ago, they claimed that they have built real quantum computer and they give possibility to use it. For enterprises, it's costly, but yes, it is available. So this is how it looks like, and indeed, they provide services to perform quantum annealing tasks. So you have some optimization problem, you run this device, you use it in order to solve it. And soon I will show you some rough ideas how it looks like in practice. Before, let's speak about quantum hardware. So now I have shown you two different paradigms of quantum computation that leads to quantum computing. So we have this gate model where you perform precise operations on your quantum particles. And second model was quantum annealing, where you have this evolution of quantum system. So you just need to adjust the system in order to find the best solution to your problem. In case of quantum hardware, well, there are technical difficulties, as I promised. We need to implement these qubits, so controllable quantum particles that will also have these effects like superposition and entanglement. So some physical entities are used, like photons, electrons, nucleus, optical lattices, quantum dots. Superconducting materials is one of the most popular technologies. For example, IBM devices use it. And We need to have a good quality of qubits, so we control them and they do not lose the state. We need to have quantity. The more qubits we have, the harder tasks we can perform. Connectivity means how many of them we can entangle and in how many different ways. So there are several parameters that are important, and each of them possess some challenges. Another thing is that usually to achieve controlled environment, more predictable one, we need to have less energy there that is interacting with it, and therefore we're making the environment very cold, so that particles are moving very slowly. And so there is a refrigerator which is like almost absolute zero temperature. And if you are asked the question, where is the coldest place in the universe? The possible answer is in one of these laboratories that holds a quantum computer. Because background, after a Big Bang, this radiation is still 1 or 2 degrees above absolute zero. But here, we're like 0.01 degree above absolute zero. So it's 100 times colder than places in the depths of our universe where there are no stars and planets around. So quite fascinating to think like which challenges people try to overcome in order to build controllable quantum particles to build a quantum computer. And so such refrigerators are used, for example, here. This is what I have shown before. So the more qubits you have, the more stable they are, the larger computation you can perform. How do we measure the efficiency of quantum computer? One of the ways is to introduce some metric. It could be a quantum volume, for example, which takes into account how many qubits you have and how stable they are, therefore meaning how large is the task that you can perform. And so this is one of the pictures that shows it. So for example, you can have not so stable qubits, and if you add more qubits, still the task will not get larger, because you will be stuck with few operations and then results become very unreliable. So this just shows us that we need both to improve the number of qubits and also the quality. And these are the possible plans. So you can think they are very optimistic, but they're very probable actually. Because we already have some quantum use cases, our experiments. Maybe it's not something in daily lives, but still we have 3 more years until 2026, so maybe we'll be there. And after 2026, it could be early quantum applications, at least in some enterprises, which will lead to commercial use. Like you have bolt application, which assigns you the closest taxi to you, or like shows which one is more efficient for you to get to somewhere. Now imagine it could be like something on larger scales that would also ping in order to receive some more up-to-date information, which is like more efficient way to use your logistics. This is how quantum computing chip can look like, and inside there are some qubits that are connected. So here you can see you have some 50 particles that are connected to each other. And these are another examples. So these are IBM, Google, and Intel quantum devices. So you can see number of qubits is roughly 50. Currently, yes, 50, 100 qubits is something that we usually operate with. This is still not enough to perform large tasks, but number of qubits is growing. Quantum devices are available in the cloud mostly because they are large, they need these refrigerators, and they're very costly. But it turns out, if you have several thousands of euro in your pocket, you can buy a real quantum device for your home. So there are experiments with different technologies. This one has some drawbacks, but it is operational in room temperature. So it's indeed possible to have a desktop quantum computer. It will be something like this, or really like a desktop device. The problem is it has just 2 or 3 qubits. So it is not possible to perform large tasks, but you see, it's still getting a bit closer. It's something that we can touch and even buy. About quantum annealers, as I said, they are very specialized, so they perform specific tasks. The upside is that we can have larger number of qubits, and one of the recent devices had 5,640 qubits. So larger tasks can be implemented of them, but as I said, there are only specific tasks that can be performed. So this is how it will look in the practice. A lot of similarities. You have a lot of wires, you have a very small device which needs to be controlled, and should be also in some environment later on which is protected from the outside interference. Alright, we have a quantum computer. It's still useless if we don't program it. How quantum programming can look like? First of all, yes, they are programmed so that you give a set of instructions that should be performed on the quantum particles. So here you can see image of dices, because you have seen that it can be also in superposition, which means some probabilistic outcomes. So it is not like a gambling or just like throwing dice to get some arbitrary random information. It is something a bit more useful. For gate model, it's almost as simple as putting blocks together. If you know which operation performs, you can just write this as instruction set, like first do operation H on the top one, then this controlled U operation on the second one, then H again on the first one, and then do the measurement. So it can be very visual programming. Those who would like to write the code, it's possible to use some libraries. This is example of Qiskit library that we also use for experimenting and also teaching our students. So you see, we write a set of instructions. We have declared that we have quantum registry of two particles, and then here we perform some operations with some parameters. And of course, it also gives us all benefits of conventional programming, like you can use loops, you can use conditionals like if-else constructions. You can use classes, functions, and so on. And instructions that prepare your circuit can be also printed so we can analyze it. So these are the operations that could be performed on your quantum computer. Or it can look like this. You can just drag and drop the operations. And here you can see example in IBM platform. It shows you the real device where it will be launched. There are some parameters. In order to explain these parameters, I give 2 or 3 lectures at one seminar that I organized this year. So this is some extra information, but overall, yes, there are some parameters. You can take them into consideration in order to think how to perform it more efficiently, because there also exist libraries that allow us to optimize it. But in the end, the programming will look like this. Just attach the operations, and they will be performed. You can use higher level programming, like calling for some procedures. For example, here, prepare Grover that uses some oracle, which is some defined operation. And then we can run the Grover routine by using this oracle for 1024 times, repeating this experiment to see our statistics of the outcomes. And another example. So we can have also some development kit. In this example, Microsoft Visual Studio, Microsoft has quantum programming language called Q#. So you see, in this sense, we are there already. We have quantum programming, we have environments, we have some small quantum devices that we can access through the cloud. How it looks for quantum annealers, as I said, in case of quantum annealing, they're specialized. They perform specific tasks. So you need to define your optimization problem, then you need to transform it into mathematical formulae. But there are some approaches, let's call it just encoding phase. So you need to encode your problem. Whereas the variables that you need to use, and also some numbers that correspond to some relationship between these numbers. After that, there is a step called graph embedding. So you adjust your problem to the connectivity of the particles in this quantum environment. So this is the step that allows you to actually launch later it on a real device. And then you can use this quantum annealer real device and observe the outcome. So encoding can look like this. This is example of the task. Very shortly, you have 4 different plants. You have 2 pods. You need to plant them in 2 different pods. Some of them are very good together. Some of them cannot live together. So this is what this table shows us. According to it, we can define these variables. This is the encoding phase. So we have +1, -1, depending on whether they're good or bad together, and 0 for those who are neutral. So this is how encoding can look like for some smaller problem. For a larger problem, you can imagine there can be a lot of variables. And this is where conventional programming can be useful, because then you can automate it. Then you need to do embedding. So one of your variables, sometimes since it is needed to be connected to some other ones in some specific way, you may need to assign more quantum particles to represent the same variable. In this example, these are these 2 red circles. This looks as a small example, but sometimes it can look like this. It may look hopeless, but again, with conventional libraries, sometimes it can be automated as well. And there also exists programming environment where you define this encoding. There are different ways how to represent it. It is possible to learn it in 1-2 days actually, even without, let's say, complicated mathematical background. It's still possible. And embedded here, there exist possibilities to use some available automatic solutions, but maybe you would like to micromanage or performance improvements. So it's all possible. So this is how programming environment looks like. So this is semi-last chapter about market of quantum computing. So how currently it all looks like. First of all, there are a lot of companies that are interested, are doing something, either research, developing the hardware, or preparing the software. You can see, for example, quantum computers, so the ones that actually deal with real hardware. And it is, I guess, not complete list. You see there are already many of those companies. So how to use some technologies, there are also some funding available, so community is growing. This is a screenshot from 2022 statistics, and you can see that many countries invest into quantum programming computing, and you see global effort is at least 30 billion. The numbers are growing. The numbers differ, of course, by sources. Here, for example, you can see 2019 it was $500 million, and it is growing at a rate 56% per year, so it's pretty fast. And with current trends, it will reach at least 60 billion in 2030. Probably the number will be even larger if you consider previous slide. But as I said, these numbers differ. For more examples, you can see something like this. Again, exponential growth, meaning that previous result is multiplied to get the next one. So you can see it's growing fast. This is how it's divided by regions. So North America, Asia Pacific are roughly 1/3 each. Then Europe, almost 1/4. Rest of the world 9%. But it's much harder to track it because most companies are international. So it's indeed world efforts, let's say, in quantum computation. So another example is that market is growing, and you can see all areas are growing, like hardware, software, and also cloud services. Company examples and provided services. We have Azure Quantum. So Microsoft allows to use applications, development kits, hardware, both classical, which can be used for some simulation, some optimization, and quantum hardware, which allows you to use all these benefits of quantum computation. Another example is D-Wave, so they give you access to their device. For example, you can pay $1,000 and use 30 minutes of quantum computational time. It's actually a lot, because operation can be performed in a few seconds and it can solve quite large tasks. So probably the price is reasonable. Another example is Amazon Bracket, Amazon Cloud Services, and they also give access to some devices. And it's very probable that very soon, within our project at the university, we will also get access to some of the devices and we will experiment with them. So it's all happening. And one more thing, since I started to speak about access to quantum devices, also it can be possible that we will work with ion trap quantum devices in Poland. So there are several technologies emerging in different countries, and some of them provide access either through the cloud or at least to some academic environment, so that people can experiment both for educational and research purposes. And very soon it will be used also for enterprise solutions. Number of jobs is growing, you can see it. Currently already tens of thousands of people, and it's also expected to grow exponentially. So some of the statistics again. IBM Quantum Experience, everyone can register there, so if you're curious, you can play around. There have also some good tutorials in order to get started. There is roughly 500,000 people already experimenting there. Number of publications is growing. Now there is more than 50,000. And there are hundreds of companies already there. One more example from my side is about QWorld. So those who have seen agenda, there I mentioned also that this is one of my first practical quantum experience. So those who are curious can later Google qworld.net webpage. Mostly we were focused on education, but also there is some research and maybe at some point also implementation for real problem solving. So we have different materials, we have webinars, hackathons, and also some challenges, study groups, pilot workshops, trainings. So, but all started with us playing with Jupyter notebooks, with IBM provided quantum devices, and we developed materials for introductory level. So that if you know a bit of Python, in 2 days you can learn basics of quantum programming to perform some small tasks. And we try to operate worldwide. In 2020, we had workshop, online one, where we had several hundred participants from 72 countries. So, yeah, those who are curious or have questions, feel free to ask about this incentive. And although this slide says thank you, one more thing is you have noticed about quantum incentive. So I'm currently also in the project called Quantum Incentive, and here you can see web page, and also can follow the social media. So yeah, we are there already. Quantum things are happening, and possibly very, very soon they will be used to solve practical tasks. And one last thing, conventional classical programming still will be demanded, so don't worry, quantum will not push away classical one, because you have seen there will be a lot of tasks where you still need to do classical stuff, not to mention that quantum programming in many cases will look very similar to the classical one. Thank you for your attention, and I'm open to questions.
Thank you. So in future, when the physical limitations and challenges are solved, do you think the quantum computer will be a separate thing, or it will be just a component in existing classical computers like CPU, GPU, and quantum CPU, for example?
This is a very nice idea, and actually I like to think about it exactly in this way, like here. So it is a quantum computational unit like a GPU, which will be specialized for tasks that are more efficient quantumly. So yeah, most probably it will be like this. At this point, these are services in the cloud which you access remotely. Later it can be incorporated inside. Yes?
If superconductors and particles are used as a qubits mostly, why are the near-zero temperatures used within the quantum computers if they reduce the movement speed of the particles and therefore should kind of reduce the performance of the computers?
So the thing is, the benefit that you obtain scales with a task. So, for example, if in classical device you solve some bundle operations in microsecond, in quantum case in millisecond, but you have quadratic speed up. After thousands of operations, it's already a benefit. So this is, let's say, linear scaling of the problem. Linearly, indeed, one quantum operation is slower than one classical. This is another reason why there will be a lot of tasks. Classical still will be efficient. The thing is that predictability and reliability of calculations is most challenging part, and it's easier to sacrifice with this speed of interaction in order to obtain this reliability. It pays off.
But is it actually reliability of the operations or the reading of the result?
So I would say all of the aspects, but most importantly the stability of the state while it is waiting. So each of the operations takes the time. The system should be intact between these operations, or while operations perform, there should be no other interference. So this is only one of the solutions to have this colder temperature. Colder temperature also allows this to have this effect of superconductivity. It's harder to achieve it. Room temperature, for example. So sadly, it is a trade-off currently. Other questions?
You mentioned a couple of facts. Fact one is that anyone can pay money to get access to quantum computers. Fact number two is that quantum calculations can crack ciphers, hash functions, etc. How come we don't have the cybersecurity apocalypse already?
So, alright, indeed, they are available. These devices, exactly this one, it's much harder to adapt it to solve this cracking problem, let's say. Therefore, we're still far from it. Existing quantum devices that can be adapted more easily, they have very few particles, like up to 50, maybe 100, but you need several thousands, which are also 100 times more stable than currently provided ones. So there's still a few years, at least, I guess, that we have. But also, there are a lot of investigation, theoretically and even practically, how to have encryption that is safe also against quantum advantages. And this is so-called direction of post-quantum cryptography. And there exist solutions also that will be stable against quantum solutions. Even classical ones can be found that will be more or less stable. So it will be sorted out. Currently, defense is better than offense. I mean, stronger.
Great, thanks.
Yes, you're welcome. More questions? Comments?
Any practical examples where you have come to something using this system?
Well, example could be with the Grover search. But it is on very small scale, like you have to find one object among, I don't know, 16 or 32. It happens faster, but at the same time, if you launch it on real device that is currently available, still it is a bit less reliable. So we need a bit larger scale in order to perform it a bit more efficiently. But some small toy examples, yes, they're implemented. One of them was the implementation of Grover search. The simplest example, you have 4 particles, you need just one operation instead of on average 3 to be sure that you have found still one element among 4. Another toy example was this one, where I have shown you quantum annealing. This one. So it will indeed show you how to place these plants most efficiently. So 2 of them will be in one pot or in another. So yeah, currently it's still 2 examples.
And that's used already. How many Q particles were required to run that test?
So that one, so you need 4 variables, but because connectivity is limited, if I'm not mistaken, 6 particles were needed. But since we have quantum annealer for this exact task, it is not a problem because this is what we had available to us, so 2000 even more. So it was not a problem for this small task. This is what I said, like quantum annealers are a bit closer to practical usage, and already some companies try to use it because it has more larger
So potentially if the matrix solutions would be around 100 to 100, still say it take the same amount of time as 44, even with this device already, right?
Could be, yes. But yeah, in general it will scale.
Yeah.
So like the larger tasks will have larger benefits compared to the smaller ones that can't be computed. So this is the point which is called quantum advantage, which many companies and research institutions are trying to approach. There are some claims that Google, for example, already achieved it in 2019, but the task was very impractical. So where indeed there was some task, quantum was solved classically, it will take much more time. Now everyone is trying to find some real-life useful task, not some theoretical number crunching.
In the Grover search example, as I understood, we are searching through a large amount of data, right?
Yes.
But does it mean that we also need to read in that data into quantum processor to be able to search for it? Like, is there maybe a sense to do quantum indexes or quantum storage so you don't have to read in that information all the time?
Yes, this is idea, like overall this information should be processed within quantum environment from the beginning. Otherwise, as you said, so I can really tell that you followed very well. Very attentive, because this was the moment when I said about input and output ideas, that you have some information, you get this as an input to the quantum system, then you process it. So if you get it as an input, then technically you already went through all this data. So this is the point when it should be already from the beginning outsourced in quantum environment. This is challenging part.
So there is no quantum storages yet? Like where you could store?
Yes, there is a topic called QRAM, so quantum rendering access memory, classical one. It's not developed yet, sadly.
So I have a question about physics. You mentioned 2 correlated particles, and if we know a state of one, so we know the state of the second one, right? So that comes against the speed of light, right? So if one particle is here on the Earth and another on the Mars, so if you know the state of this one, so immediately you know the state of another one. So but speed of light is much lower than distance between.
Yes, so first of all, I'm a quantum computer scientist, but my physics background is not, let's say, I didn't attend the courses of quantum mechanics, but I have some basics. How this paradox is solved? First of all, you don't get any extra information at this point, because if you knew from the beginning that they are correlated, then technically you don't get any new information. It is like you had 2 coins, you tossed them, but you know that they were glued all together. Same moment. So, as I said, you don't get new information. If you want to communicate to others, you know when you will measure, you will get the same outcomes I had. You still need to communicate it classically. So in this sense, you cannot be faster than speed of light. There is idea of quantum teleportation, where you perform some operations and the information from your one particle get teleported to other one. In this case, you still need to send some classical information, and still you cannot exceed the speed of light. So in this example, sadly, you don't get any extra information. An example of quantum teleportation you will get, but you still need classical communication at below speed of light. So currently there is nothing broken. And most probably it won't be possible. But we'll see.
Okay, thank you. I suggest if you have some more questions, then come in and break the Maxim, and I assume you will still answer.
Yes, I would like to answer.
Thank you very much for your